Now let's look at an example, and I think this is a relatively straightforward concept of center of mass. So we'll just look at one example, and we'll go to 2D. Okay, so we've got the formula in 1 dimension, and we can upgrade it to 2 dimension very easily. So instead of, remember, in 1D, it is XCM is sum of MI over sum of MI. Right? Or you can write that as MIXI from 1 to n, obviously, just lazy, and capital M, that's the total mass of the system. So you just take the X and upgrade it to the position vector. So instead of 1 dimension position, you have now a 2-dimensional position or a 3-dimension position. And you can do from 1 to n like this, right? And MIRI, okay, and just capital M like this on the bottom, or sum of MI like this as well, either way. Okay, so let's see if it works in higher dimension, because if you can do this, you can do the 1-dimension case easily. So this time we'll need an axis like this. Let's say we have 3 masses here, here, and here. Okay, so let's say this is at y equals to 3 and x equals to 6. Okay, all right, so it is at position, each of the position. All right, so let's figure out what is the center of mass. In fact, before we chug in just the numbers, do you have an intuition? If I have 3 masses here, let's say each of them is 10 kilograms. Okay, 10 kilograms like this. Okay, where would the center of mass roughly be? Can you get an intuition for it? Just even before you plug in the numbers. Well, if this is a triangle, right, the center of mass, so imagine if you have a whole triangle piece of paper, where's the center of mass? Probably somewhere in the middle of the triangle, right? Some sort of average, especially if these are the same mass, somewhere here, all right? So let's see, I don't know, let's maybe somewhere here, probably a little bit higher, we'll see, right? But somewhere inside the triangle, okay? So let's say this is x and 3. Okay, so let's see if the formula gives us what we expect. Okay, how are we going to do this? So we'll just apply it, right? So M1 is, so we're going to write M1 R1 plus M2 R2 plus M3 R3 over, and the total mass, right, over here, which is just M1 plus M2 plus M3. And now we will plug these in. Let's see, is there anything I can do simplify before I plug in number? That's always a good question to ask, right, before plugging in the numbers, and probably not. All right, so we'll go ahead. All right, so M1 is 10 in SI units, and R1 is the position vector of the first mass. So we'll need to label which one's 1, 2, 3, right, in your working. So we can actually talk about whoever's grading your work can actually understand it and give you the correct grades, right? So let's say that's 1, 2, and 3. So for 1, what's the position vector? What's the position? The position vector is the vector from the origin to the object, right? So the object's here, so the position vector is 0, 0. Okay, and M2 is 10 again. What's the position vector of M2? Well, that's 6, 0. All right, so X is, so that's R2, and that's R3. Okay, all right, so plus M3, which is 10, and R3 is how many units X? 6 units, and 3 units Y. Okay, good, and divide by so the mass is 10 plus 10 plus 10, right? So if you write it like this, the TAs will be able to follow exactly what each variable is and see if you plug in the correct. So if you made a small mistake here, you might lose 1 mark, but not completely, right? So so that's a good habit to develop. All right, so this is just 30, and in fact, everything's going to be divided by 30, so we can even put that out front. And these are all 10. I can actually factorize that and have it as 10 times whatever that is. Okay, so 10 times 0, 0 plus, let's just clear this up, use a different type of brackets. Okay, 0, 0 plus 6, 0 plus 6, 3. Right, these are the position vectors. All right, so what do I have? I have 1/3, and inside the brackets, I have 12. So I have a vector of 12 and on the bottom 3 like this. Okay, so I don't need that redundant brackets. Okay, all right. And now how do you deal with having a number, a scalar in front? You just multiply that in, right? So you have 12 divided by 3 is 4. 3 divided by 3 is 1, right? So RCM is 4, 1. Okay, so where's 4, 1? Right, so 4, so this is 6, so 4 is roughly here, right? So right, 0, 1, 2, 3, 4, 5, 6, roughly, right? Okay, roughly here, and 1, 1, 2, 3, right? Roughly here, exact, and you see that 4, 3 is exactly, it's at least inside the triangle and exactly what we expect. Okay, so that's really it. And another way you can see how sometimes if you look at the textbook, you see it actually split into the X and Y components. You can do that as well. So what if let's see, if I keep it general, if I don't plug this in, right? If I don't plug in the numbers and just say this is X1 and Y1, X2, X3, right? Y2, Y3. So that's the position vector for 3. That's a position vector over there, position vector over there. And if I keep that, let's keep all these variables like this. Right? So that's just capital M, but this is M1, M2, M3. So you can see on this side, I can write XCM and YCM. So this is the position vector of this guy. So just the X component and Y component. And if I multiply this in, you can have, they all have sort of a common factor of 1 over M in front, right? So you have M, X1, X2, plus M1, M2, X2, Y2, right? M3, etc. X3, Y3. Okay, I can multiply the M in here. I'll separate in a separate step. So M1 over M of X1, X2, Y1, plus M2 over M, X2, Y2. I won't write the third one, just to save a little time. And here, I can multiply this in. So I have M1, X1 over M, M1, Y1 over capital M, plus, but plus is just, I can just add all of these together. So it's M2, X2 over M, plus M2, Y2 over M, plus the third one, plus the one with 3. And I have M1, X1 plus M2, X2 plus M3, X3 over M. And the bottom, I have M1, Y1 plus M2, Y2 plus M3, Y3 over M with XCM and YCM. Okay, so what did I do? What do I learn from this? Is XCM, the center of mass, the X center of mass is really the center of mass formula for the X components. And the center of mass in the Y direction is just the center of mass formula or the definition in the Y direction. All right. So there's 2 ways to do it. You can do it in the full glory vector form, or you can do you can just split into X and Y components, look at them separately. And as usual in a lot of physics, as you can see, the X direction effects does not affect the Y direction effects. Okay. So that's a example of this. You can look at your textbook, example 9.14, 9.15, these 2 examples and see more details. It's a relatively simple concept. Yeah, and we'll move on to look at moment of inertia.